Hey everyone, welcome to yet another episode of Read AI with me. And today in this episode, we're going to be talking about one of the most famous methodology in explainable artificial intelligence, XAI, and it holds a certain amount of weight in industry practice. So, before we get started, I want to say that me personally, I had a lot of fun reading this paper. It's not really a super complicated methodology per se, but it uses a very straightforward methodology, which includes blocking up certain information of your data and simply examine how the performance change. And in doing so, you get a sense of whether that blocked information is useful or not by looking at the results before and after you blocking the information. So it's kind of a very intuitive methodology that if we're just talking about you and I will have no problem understanding it. And it's really interesting to see that the team led by this group of researchers at Boston University actually laid out the theoretical map of how to carry out this sort of analysis. So with that being said, let's get started. So let's start with the title. The title says RISE, which is short for Randomized Input Sampling for Explanation of Black Box Models. So immediately right off the bat, I think the keyword here is randomized. And this randomized input sampling is essentially a carry out the information of, hey, we want to do something with the input data and it requires random sampling. Okay, and specifically we want to explain black box models. So that's great. The leading author here is Petsiuk, and he led a team at Boston University, and this is their paper. As you can see, this paper was published in 2018, so not that long ago. Let's take a look. Deep neural networks are being used increasingly to automate data analysis and decision making. Yet their decision making process is largely unclear, that's the keyword, and is difficult to explain to the end users. Now that's a good point, right? If my deep learning algorithm consists of 50 or sometimes even hundreds of hidden layers, it is going to be very challenging to explain to user exactly how information passed from one end to another. Something like that, it's going to create a lot of problem. Specifically, if we can't really explain the features, then the decision-making process is going to be a hard sell, even if it can be achieved with high prediction performance. So immediately, I think this paper is hitting on a very important area. Let's take a look. In this paper, we address the problem of explainable AI for deep neural networks that takes images as input and output the class probability. We propose an approach called RISE that generates an importance map indicating how salient each pixel is for the model's prediction. In contrast to white box approaches that estimate the pixel importance using gradients or other internal network state, RISE works on black box models. And I think later on in the paper, they said that it actually works on any black box model. So that layer of flexibility is something that's going to make this paper a good sell. It estimates importance empirically by probing the model with randomly masked versions of the input images and obtaining the corresponding outputs. We compare our approach to the state-of-the-art importance extraction methods using both an automatic deletion insertion metric and a pointing metric based on human annotated object segments. Extensive experiments on several benchmark datasets show that our approach matches or exceeds the performance of other methods, including white box approaches. So I think right off the bat, this abstract, it's very well written, and it already gave people and audience a clear picture what is going on, right? They have a methodology that's model agnostic, works on any black box model, and specifically, they're really just trying to mask certain part of the image, and they observe what is the results before and after that certain part of image is masked. And how do they generate these masks? As you can probably guess, they generate these masks randomly, right? So I block off portion of the images randomly, and before and after the block off, which they call deletion and insertion, they simply look at the prediction performance and they see how it changes. So I would say it's a very straightforward paper, And the first section is just the introduction of the field, right? There's great amount of success in deep neural networks, leads to remarkable growth. And in spite of all this success, it is yet unclear what is going on in the decision-making process. And perhaps, it leads to some challenges of how to generate that decision. So let's take a quick pause and dig a little bit deeper into what that means. Neural network consists of neurons. Let's say I have a neuron like that, and then I have another neuron like that, and perhaps another neuron like that, and I can call them x1, x2, x3. Let's just say, for simplicity, there are 3 variables. And the task is easy. I want to build a neural network that makes some prediction. So the first thing I will do is I'll probably have a weight, go something like that, and I call it W1. And then I have another weight come down here, W2, and then I have another weight, W3. These weights, along with the input variable x, form a linear combination. Okay, so if I may, I can draw a big circle, and in this circle, there's going to be a linear transformation and an activation function, which I'm going to denote as A. And the linear combination is simply going to be a summation. I have this running index j from 1 to 3. And I'm simply using wj and xj to form this linear transformation. And if you write that out, it can simply be w1x1 plus w2x2 plus w3x3. Now you might observe that, hey, where's the bias term, right? That's exactly true. I'm assuming there's no bias, which means if I have a plus b there, then I'm assuming that doesn't exist. So that's the linear component. Now what happens to this activation function A? This activation function A, which is the nonlinear part, let me write it here. This nonlinear function, I need to make a choice. I need to choose this to be some sort of particular setup to mimic the structure of a simple logistic regression in a generalized linear model that we all learn in Stats 101. The activation function here can simply be a sigmoid. So here we can say, I'm going to define this as sigmoid. So if this is alpha as an input, then it's a sigmoid as alpha. This is defined. So with this definition, this can be defined taking the form of sigmoid function, which goes like this: 1 over 1 plus exponential minus alpha. Okay, so now we said that there's a linear transformation first. Well, as you can probably guess, we're throwing this summation, this linear transformation, into this activation function. So this is going to equal to 1 over 1 plus exponential. Instead of alpha, we're going to plug in the results of the linear transformation. So this is going to be summation j from 1 to 3 wj xj. And this is going to be our activation function of x and w. Now this is a vector, this is a vector, so it goes like that. Now the output of this, we're going to give it a name. It's simply going to be the predicted value of your label, or your probability that the observation is class 1. So let me put a y hat here. That's going to be the prediction. So I'm going to say this is prediction. Okay? This entire process from x all the way to y hat, it's called forward propagation. So let me make a big remark. This is going to be forward propagation. And I'm going to give it an arrow. It goes from left to right. Okay, so it starts from the input, and then the information passed down here goes from left to right from each and every neuron, and then in the end it goes through this linear transformation and nonlinear transformation, and then at the end of the day it produces a y hat. So that's going to be the forward direction. Now what about the backward direction? There's also that, right? In order to execute the backward propagation, the first thing you need to do is to compute the gradient, which is essentially a partial derivative of the loss function. So first of all, we want to check out our errors, right? So we want to understand our error. So how do we do that? Well, the proposal is to use a loss function, which is this calligraphic L that consists of your prediction and the truth, which is y hat and y. Now this loss function is also going to be a choice, right? It can be L1, it can be L2, it can be hinge loss, it can be whatever, right? So I'm just going to be a little bit easy. I'm going to choose square loss. So here I'm going to say square loss. And then that's your y hat and y. I'm going to use this running index I to denote the observations from 1 to n. This n is a sample size in the training data. And the formula goes as this: y hat I minus yi and square. That's going to be the square loss. And this loss function that's taken this form, we can compute the gradient, right? Specifically, we can compute the gradient with respect to your w. So now the goal is really to minimize your loss function by choosing w. And that's really the goal here. Now, since your loss function takes a particular form, then this really becomes argmin by controlling your w, and it's exactly the summation I from 1 to n yi hat minus yi square. And this is the goal. This is how we train the machine. We want to minimize this exact value, okay? And then how do we do that? We need an optimizer, right? This optimizer is essentially an algorithm that changes your w according to certain rules so that this goal, this loss, it's small, okay? And exactly what do I mean by that? For example, you can choose gradient descent. At each step s, we first compute gradient of your loss function, and then we update your w at the step s to be w from the previous step, s minus 1, minus learning rate eta and the gradient of your loss function. And this way, every step s can be like 1 or 2 or 3 or 1,000, right? Every step you update your w, and by using this gradient, hopefully this w gets closer and closer to a certain set of w, such that this gradient, this loss function, doesn't change that much. Okay, so this framework is called backward propagation. So let me put the name here. This is going to be backward propagation. So exactly what's going to happen is, let's say I have a graph like this. I have an x-axis and a y-axis. The x-axis is epoch. Specifically, one epoch consists of one forward propagation and one backward propagation. So it's like this process that I roll up here from left to right and then from right to left. It goes one full cycle once. That's considered one epoch. And as you move above epoch, as you train your machine, you will observe that your accuracy goes up, right? So it probably starts from here and then eventually it goes up. So hopefully sometime in the future it flattens out, and that's gonna be the indication that, hey, your algorithm probably already converged, right? It hits a certain error threshold that maybe it doesn't increase anymore. Then you're done, right? That's when you stop the machine. So this kind of setup, it's a very simple neural network. It's a one layer, one neuron, and that's it. Once we finish training and we're done with finding this w, we get a certain set of w, right? So maybe after you're done, w1 could be 20%, w2 could be 30%, and w3 could be 50%. And that's going to be a set of weights telling me how much this x1 affects the final outcome y hat. Now, if I may, and once this is done, I can probably write y hat to be 1 over 1 plus exponential, and then here maybe I have 20% x1 and 30% x2 and 50% x3, and that's my sigmoid function. And perhaps I get some intuition of how this weight affects your y hat. But that's only because when this model is easy, and this is extremely easy. There are only 3 weights, 3 parameters. Now the issue is, what if this thing is hundreds of layers? So in this diagram, I only draw one hidden layer. What do I mean by that is, this might be your input, this might be hidden, and this might be your output. And check this out. let's say I have x1, x2, and x1000. And this hidden layer 1, maybe I have A11, this is maybe A12, and perhaps I have A120 if I have 20 hidden neurons in this hidden layer 1. And then maybe I have some output, right? And this output, maybe I call it Y1 hat and maybe Y2 hat. Even if I just want to check out this Y1 hat single neuron in the output, I have to go through all of these A1s like this. And each of the neuron in hidden layer 1, I have to go through each of the X, which means I have to go through like this. Okay, once I'm done with A11, I move on to A12. So I have to do this. Now, as you can see, this goes all the way in the end to the 20th neuron, and the information goes like this. Now that's going to be convoluted, right? If I want to write this out, it'll probably take 20 pages. And eventually, sometime in the future, we get tired, we lost track of the progress, and we don't really know how information is passed from left-hand side to right-hand side, right? So what I mean is, if I have some information here that's important, how does this X1 transfer from left-hand side to this Y1 hat on your right-hand side, right? Exactly how does it go? Does it go to A11 first and then go here? Or does it need the help from X2 and then go to Y1? Or maybe it comes down to A12 and then goes this way, right? Which way does it go? We don't know, right? It's very challenging to explicitly state how this X1 affects this Y1 hat. So you can see now, as this architecture gets deeper and deeper, it just means that this hidden layer, it's not 1, it's probably 100 or 200, right? Then take a leap of faith, you can kind of see that this thing gets immediately out of hand. And it's difficult to say exactly how information is passed from X1 to Y1 hat. We don't know that, right? It's very difficult to explain to an average user of neural network of how information is passed through. And that's a problem. So this is why in the first section, the author really trying to lay out what is going on in the field and why this field is important. And specifically in the domains where decision can have serious consequence, right? We're talking about medical diagnosis, autonomous driving, criminal justice. If somebody is on the bed and you're giving him a surgery, you really want to understand what's going on from left to right. You don't want to say, oh yeah, here it's a 50-layer neural network. It tells me to cut open your brain and take something out. I was just going to do it. Or in autonomous driving, there's also same issues that require a lot of debate, right? You don't want to just say, oh yeah, this car is just going to keep moving forward. We don't know if it's going to hit anybody, but it's going to keep moving forward. And it's because this 50-layer neural network tells us so. None of these statements, even though it's correct on average, with a high percentage of accuracy, it's not going to hold on the table, okay? In industry practices such as medical diagnosis, autonomous driving, criminal justice, it requires more of that. You don't want to send somebody to jail because the 100-layer neural network tells you so, okay? So we're hitting an important spot here. So specifically, what this paper is proposing is, okay, we have a problem. We don't really understand which features are used, right? Which X1, X2, X3 are used to generate that prediction. Well, what do we mean by that? In image data, we're talking about the image with certain labels, right? Let's say the first image here, we have sheep. That could be a label. Sheep is in the image, right? It's a clear label. So now you're going to train a piece of AI algorithm to make some predictions. Well, it either says it's a sheep or it doesn't say it's a sheep, right? It could probably say something else. So if it is correct, or it doesn't matter, it could be wrong, we want to understand why it's correct or wrong. And that's really the story here. And in this paper, I don't think it defines what is XAI, but the direction that it took to demonstrate what XAI means is essentially drawing these importance map, highlighting how salient each pixel is or how salient a location of pixels are on the picture. So we talk about this sheep as a label in the picture, right? And if it wants to make a prediction that the label is, that the AI is going to guess that the label is sheep, it better uses the area of the sheep. Not because it's on the grass, not because it's drinking water, not because anything else, but because the location that this neural network investigates on the picture is precisely on the area where the sheep is. I don't think that we have definition to define XAI as this aspect, but I do believe that's the angle that this paper took. What does it mean when you have the explainability power to say, hey, I know what this black box algorithm is doing, right? Whether it's right or wrong, at least we have one direction that we can take to try to understand it. And I think that's extremely important. And same with the second picture. You see, it could be a bird, it could be a person. Now, obviously, in this picture, it looks like a bird. So if your AI is going to guess that this is a bird, it better say that it's a bird. And it better look at the area where the bird is. Not because it's a forest, right? If you're going to look at the forest and you're going to guess it's a bird, that doesn't really mean that your AI is awesome. It just means that you're taking a shot because it's a forest. So that's kind of the situation that we want to avoid, even if in this case your AI guessed correctly. So how does this proposed algorithm RISE answer this question? Well, first of all, I want to start with a couple of existing methods, sort of like a literature review. A common practice will compute importance for a given base model and then output a category. And however, they require access to the internals of the base model, such as the gradients of the output with respect to the input, intermediate feature maps, or the network's weights. Many methods are also limited to certain trained network architectures or layer types. In this paper, we advocate for a more general approach that can produce a saliency map for an arbitrary network without requiring access to its internals and does not require re-implementation for each network architecture. And the contrast is LIME, which I believe in my previous episode we talked about this methodology, and it offers a black box approach by drawing random samples around the instance to be explained and fitting an approximate linear decision model. So the keyword here, I believe it's a linear decision model. However, its saliency is based on superpixels, which may not capture correct regions. Now that's going to be important. So what does it mean by that? You can kind of look at this picture, right? First picture, this is a picture where perhaps, this is the picture from the author's point of view. It's an example where other methods probably didn't really work well versus the proposed methodology worked, right? So this picture in front of us on top left corner in the location A, it's a input picture. It's probably a bowl with a bunch of fish in there, right? Goldfish. So if you're going to train an AI that successfully predict the bunch of fish in there, then you better look at the location where the fish is, right? So the demonstration here is that the author showed successfully in picture B, the second one on top, which is the proposed methodology RISE, worked. When we look at the location where the fish is, there are certain highlights, right? There are red, yellow highlights indicating that's where the fish is. That's a saliency map that tells us exactly what is the location that this AI used to make a prediction. Versus if you look at C or D, it doesn't quite tell us where the fish is. And that's due to the algorithm structure of C and D. Somehow, it doesn't quite work with this kind of picture information. Specifically, we have information from the picture that's corresponding to the correct label, that's in different shape, different sizes, and scattered around all over the pictures. Right, this fish on top, it's a completely different shape than this fish on the right, and versus this fish on the left bottom corner. And that's going to be an area where, according to the author of this paper, RISE, says that it has advantage to. So how does it show that? If you use RISE, and you insert the features or you delete the features, there's a certain score, right? There's a certain guess of the probability that this thing is fish, right? If you cover up the information that's important. Important here means that it has a direct indication and it helps making the prediction correctly, then perhaps the performance drop, which is what they're really trying to show here. AUC, it's a value that indicates how accurate your model is. And that's sort of the idea that this paper is trying to attack. Versus if you use other methods, say this gray can or this lime, then maybe the AUC doesn't drop that much, which means you're not really covering up the area that has direct impact on the prediction. And I think this presentation here in this figure is quite clear. It's quite clear. So now this is a big picture that we understand what's going on. Now let's take a look at the algorithm. This is the algorithm of RICE, randomized input sampling for explanation. And specifically, it's talking about these MIs, these matrices MIs, which essentially just a bunch of randomized masks that's directly drawn from Bernoulli distribution. Okay, so Bernoulli distribution is 0 1s, right, with probability 50. It's like a coin toss, right? So each position of the mask, it could be black and white, right? For example, this spot, this area are white, okay? And these areas are black. And these areas are completely randomly generated, okay? Each of these masks, we can cover it up on the picture. So what do I mean by cover up? These black areas, once it overlays on the original picture, then perhaps it covers up certain area of the picture. Here's an interesting question. The areas that you covered, is it good or is it bad? Does it pose a roadblock for you to make a prediction or not? So let's take a look at this picture. The first mask, there are certain area on the maybe in the middle or maybe to the right, and then it perhaps covers up the body of the shark. Okay, so now we go to this black box algorithm and it gives you a certain probability that this picture is shark. So let's say your original image is I, and if you mask it and this I circle MI, okay, this I circle MI is essentially a picture of shark, but with certain parts of picture covered, okay? So now we can make two predictions going to this black box. If you throw in the original image I, then the probability that this thing is shark, given this x equals to I, might be 0.99. So there's a high probability that the original picture I, which looks like that, is a shark, okay? Now, what's gonna happen is, I'm covering up certain area of the picture. So this y, so probability of y is shark, given x is I circle mi, this might be 0.09, as it says here. So now there's a problem, right? If you're gonna drop from 0.99 to 0.09, that's a pretty big drop. So that will probably tell us that whatever this area that's covering, it's probably very important, okay? And as you can see, intuitively, it kind of is, right? If you're gonna train an AI to predict that there's a shark in the picture, then there's better be a shark in the picture. If you cover up the shark, then the AI is not gonna recognize that there's a shark in the picture. So that's kind of the reasoning that we're trying to understand here. If the score dropped a lot by covering up certain area, then that kind of indicates that the certain area that you cover is important, okay? And that's just from one map. And they generate randomly where these areas are on each mask. And they do it many, many times. Then hopefully overall, it gets a certain many layers for every single location of how many times it's covered. You overlay all of them together, you can kind of get this saliency map that looks like the one on the right, which says, hey, there's a shark in the middle of the picture because across all these mask pictures that we covered randomly, on average, if I cover up in the middle, it drops the most. The score drops the most. That pretty much gives me a conclusion that, hey, the middle of the picture is important. You probably shouldn't cover it up. And that's really the key algorithm, the key essence of this proposed methodology, RICE. Now, if you go down and take a look at a couple of examples, So that's another example that the author is showing us, right? Let's say this is a picture and there's a bird in it. The bird is bitten. Bitten is not biting something, which I actually made a mistake by interpreting it in the earlier recording. It's really the type of bird. And because the label is type of bird, and if you're going to train an AI to successfully predict that there's a bird in the picture, then the AI better be looking at the bird in the picture, not the fish, not the lake, right? Where that's probably the location that this bird frequently feed off the fish in the water. And perhaps that's how the photographer take the picture. Perhaps you train an AI not by recognizing the bird, but by recognizing this is a lake where there's fish in it, right? So this kind of issue, according to the author in this paper, you can use the proposed methodology RISE to address whether AI is predicting the right thing by using the right features. And RISE is able to tell you, okay, you look at the saliency map, the bird's head is highlighted, and that's the bird that we want to predict. You remove that part of the picture, the performance drop. Okay, so what do I mean by drop? Drop means your performance is down to no more than 5%. So if I block the bird's head just like that, then this neural network is probably going to tell me, oh, the probability this is a bird is no more than 5%. Very little chance this is a bird. The reverse is also true. If I uncover this, and perhaps I block something else, doesn't really matter, but as long as I have this part of the bird's head uncovered, then the AI is going to say, oh yeah, the probability that this picture is a bird, is this type of bird bitten, to be 85%. That's a huge jump from 5% to 85%. That's a huge jump. That means this certain area is important. It's where the bird is. Now, conversely speaking, same situation. If you train an AI that want to predict the bird and you use RISE, it came up to be the fish or the lake or the water where the bird constantly feeds off from, then we have a problem. Then you simply train an AI to recognize the lake where the bird constantly go there and eat fish. You didn't really train an AI to predict a bird in the picture. And this kind of thinking process allows us to truly understand and explain what do you mean by having a successful prediction. And as you can see from the second picture or from other examples before in the previous section of the paper, we can kind of get an understanding the author's point of view of what do we mean by saying a piece of artificial intelligence model is explainable. So I think that's kind of interesting. And here's another picture that's later on in the paper that instead it's on the image captioning. So for example, you could have a picture that have horse or that have a horse carriage or building or whatever that looks like New York City, and then maybe you have the captions of the picture says a horse and carriage on a city street. And this sounds like to me it's a multi-label classification where you have one picture corresponding to perhaps more than one labels. Horse can be a label, carriage can be a label, perhaps the color white can be a label, right? So this figure 5 gives us a small presentation of a more advanced usage of the proposed methodology RISE. Now, according to author, this proposed methodology RISE can also be used on multi-label classification. For example, where in picture B, you can look at the horse by itself, and that gives you the area of the horse. Or you can look at the horse carriages, then maybe instead of looking at the horse, you look at the thing on top of the horse that's connected to the carriage. And if you want to look at the color, the RISE also does color as well. Then perhaps the only thing that's color white is the building. And that gives you maybe the horse and also the building in the background. And this further illustrates the advantage that the proposed algorithm has over many other algorithms. And it works with ultra deep learning models. For example, VGG16, RaiseNet, these two algorithms both have millions of parameters. Like we're talking about huge amount of training cost. And you don't want to train a machine and then in the end of the day you can't deploy it because you don't understand what it means. Well, luckily we have RISE, and RISE help us to understand that. And that's pretty much the end of the paper. As you can see, it works for any black box model and it's jointly related to DARPA XAI program. So there you go. I hope you enjoy reading this paper with me, and hopefully this paper gives you more insight about how to explain a neural network architecture, specifically when the data is in picture format. And I hope you have fun. So have a good day, and I'll see you in the next episode.